Do you feel like a coffee break? So do I. What about we talk about the linked list versus ArrayList debate, a subject that shows up quite regularly here and there. You may be wondering what implementation should you use. So let me show you how you can make the right decision for your application. You will learn about performances, memory consumptions, pointer chasing, big O of n complexity, all these good things with precise JMH benchmark that will help you make the right decision for your application. There are a number of misconceptions you can read here and there about the differences between ArrayList and LinkedList. These implementations have been designed 25 years ago, and many things have changed in the meantime. Some of the things that were true at that time are not true anymore today. One of them has to do with the complexity of the different operations that list has to offer, often described as being big O of 1, big O of n, or even big O of log of n. So maybe we can start from there. What does all this gibberish really mean? Does it matter for your use case, for the actual code and the actual data you are using in your application, and how you can use this information? Let us examine some of the most used operations on list. Let us choose 3 basic operations, getting an element from the list, and we'll see 3 places to read from: the beginning, the end, and the middle of the list, iterating over the elements of the list with the 2 patterns you can think of, iterating with an index or with an iterator, and inserting an element at the beginning, at the middle of a list, and at the end. Okay, inserting at the end is not really inserting anymore, it's more adding at the end. You could also think about replacing the first element or the middle element of a list, but the cost is actually the same as reading it. If you remember your 101 course on arrays and linked list, you may remember the following: the complexity of the operations on arrays and linked lists. What does this obscure notation big O of 1 or big O of n really mean? And does it apply to your use case? Can you use that information to choose an implementation over the other? This big O of n notation means that past a certain threshold, the time it takes for the algorithm you're working on to process your data is proportional to the amount of data you are processing. Simply said, if the amount of data you process is above this threshold, doubling this amount also doubles your processing time. And the important point there is if the amount of data you process is above this threshold. And how can you know the value of this threshold? So for n greater than your threshold, the processing time is alpha n. That works well if your real formula is, for instance, alpha n plus beta. Suppose that beta is equal to 1 and alpha is equal to 10, then past the threshold of 10, if you say that your processing time is just n, the error you make is less than 1%, which is probably okay. But if alpha is 1 and beta is 10, then to get a 1% precision on your computing time means that your threshold is not 10 anymore, it's more like 1,000. The point is, knowing that your complexity is big O of n is interesting, but you need to know more. How does it apply to your use case? What is the value of this threshold for your application? If the threshold is 1,000 and you are processing 100 elements at a time, then this formula doesn't apply to your use case. You need more information. When it comes to performances, there is only one principle: measure, don't guess. So this is what we are going to do. Linked list and ArrayList are not working in the same way at all. There are hidden mechanisms internally that have an impact on performances. And if you want to take an informed decision, knowing them will help you. Before we start, let us take a look at some benchmarks. All you are going to see has been done with the only tool you can use to bench your Java code, JMH. JMH stands for Java Microbenchmark Harness. I put the link in the descriptions. It has been developed for years by Alexei Shipilev. You will find a link to his very interesting blog in the description, as well as a talk he gave years ago at Devoxx Belgium, where he explains why it is so hard to properly measure the performances of a Java application and why JMH is the only way to go. And yes, it means that all the benches that you can see here and there that are using loops and system current time in millis or system nanotimes are just wrong. Don't lose your time looking at them or trying to explain them. And don't rely on them to choose an implementation over the other one. The first benchmark we are going to look at, just take a list and reads the first element of that list. The second one consists in reading the last element of the list. And the third one consists in reading the element at the middle of that list. And we're going to run these benches for several sizes of lists, from 10 to 10,000. So here are the results. For the reading of the first element, what does this table tell us? It tells us that it takes about 1.2 nanoseconds and that the error on this measure is less than 0.1 nanosecond. This error tells us that if we redo this bench a lot of time, and this is what I did to compute the statistics, 90% of our measures should be between 1 and 1.2 nanoseconds. So we can draw two conclusions from this bench. First, there is no difference between an array list and a linked list when you need to access the first element of the list. And second, the amount of elements in the list has no impact on this performance. And this is only logical. ArrayList has an internal array, so you can access the first element of this array directly, where LinkedList has an internal direct reference to the first element of its internal linked list. So let us now take a look at accessing the last element of the list. We do not expect any difference for linked list, because it turns out that linked list has also a direct reference to the last element of its internal linked list. For ArrayList, it could be different, because we are now accessing the last element of an array instead of the first one. So is it more expensive or not? So here are the benches. And there is actually a tiny difference between the benches. Is it significant? If we just consider the raw numbers, it is, because the error is very small. But we are running on a CPU that can't do much more than one operation every nanosecond. So this sub-nanosecond difference is actually not really significant. The conclusion is twofold. There is no difference in accessing the first or the last element of a list, whether it is a linked list or an array list. And the amount of elements in the list has no impact on this performance. Let us now access the element at the middle of the list. For ArrayList, we do not expect any difference than accessing the last, because it's just about reading an element of an array using its index. For linked list, the situation is different. There is no more direct access to the elements of a linked list. As you know, to reach a random element in the middle of a linked list, you need to start at the first one, then the next one, again, until you reach the element at the right index. Linked list has an optimization. If your element is closer to the end of the list, it can start from there and then go backward. But it is still jumping from one element to the other. Is this operation expensive? Well, there is only one way to find out. Let us bench that. And you can see that for ArrayList, the situation is the same, with a difference which is not really significant. For linked list, on the other hand, the situation degrades very quickly. Even for a small list of 10 elements, reaching the fifth element is significantly slower than for ArrayList, by a factor of 2. Could this factor of 2 be bad for your application? Well, you are the only one who can know that. On the one hand, it's a factor of 2. On the other hand, the difference is 1.5 nanoseconds, which is still very small. So maybe it's not too bad. For 10,000 elements, it takes about 8 microseconds to access this element. So that may be a performance hit for your application. Where does this difference come from? Well, it comes from something that did not exist when linked list was written, which is called pointer chasing. It's not that pointer chasing did not exist in the 90s, it's more that it was not a problem at that time. It has to do with how the cores of your CPUs access your data. Your data is in the main memory of your computer, and it has to be transferred to the caches of your CPU. In the 90s, there was no cache on CPU, so this problem did not exist. Your CPU now has several levels of cache, smaller and smaller, and faster and faster. And what you want is to have your data ready in your cache before your CPU needs it. It turns out that the content of the main memory is transferred to the different levels of cache line by line, a line being a certain amount of memory. The size of a line depends on your CPU. It's probably 64 or 128 bytes, that is 8 or 16 longs. Because an array is stored in a contiguous zone of your memory, knowing the address where the middle element sits is easy, and you can transfer the correct line of memory immediately in your cache. On the other hand, the address of the middle element of a linked list is only known by its previous element. So to get to it, you actually need to traverse all the references from the first element to the one you want to reach, one by one. You are following one pointer after the other. This is called pointer chasing, and this is what is costly. There is even a simple way to show that with linked list. The bench rerun actually creates the linked list in that way, and odds are that the node objects created with linked list for each iteration are actually nicely stored in contiguous zones of the memory. Meaning that when you move one line of memory to the cache, you probably bring another node along with it. Could we prevent that and see if it has an impact on the performances? To do that, you can create more nodes that you can put in another linked list between the creation of two nodes, and adjust this number to create more space between the nodes you are looking at. You could create a new linked list in that way and launch the same benches using different value for this sparse index parameter to see the impact it has. And here is the result. If you spread your nodes in your memory instead of storing them in a contiguous zone, the impact is roughly a factor of 3. You go from half a microsecond to 1.5 microsecond. It is certainly significant and gives you an idea of what to expect in a real application. Now the question is, once again, is it bad for your application? And only you knows that. But I still think that it's better for you to be aware of that. How is iteration working with both implementations? Well, as you can expect, pointer chasing will not play nice with linked list. You have two patterns to iterate over a list. You can use an index and increment it between 0 and the size of your list, or use the for each pattern, which internally creates an iterator. Now, you may be thinking, an iterator, that's one more object. Do I really need it? Object creation is expensive. Will it hurt my performances? An index is a primitive type. It must be much more efficient. No? Well, let us see that. If you have an array list, Both patterns are basically the same, which is by the way expected because if you check the implementation of Iterator that ArrayList gives you, it is in fact using an internal index. So the performances are roughly the same, and yes, this is indeed expected. Be careful on this table because we are now talking microseconds and not nanoseconds anymore, so that's the difference. What is also expected is that iterating over a linked list with an index is probably one of the worst ideas you may have when working with linked lists. Here is the bench, at least you saw it. If you do that, every time you want to access an element, you need to traverse all the list again until you reach that element. So don't do that. Use the for each pattern, it will work much better. And stop thinking that creating objects is expensive. Are you sure that the JVM will create this iterator at runtime? No one is taking a reference on it. It's confined in this block of code. It cannot escape it. Suppose the JVM actually doesn't create it. Who is going to notice it? And the second thing that is also expected is that iterating over an ArrayList performs better than a linked list, once again because of pointer chasing. It's not too bad, but you still have a factor of 4 between both. Actually, because the difference is so significant, you may be wondering if it could be more efficient to first copy your linked list in an array-based list first, and then process that list. It could be interesting only if you plan to iterate several times on these elements, or if you need to access them randomly by the indexes, and of course, if memory is not an issue. Creating the list itself with this pattern is in fact negligible compared to the time it takes to iterate over your linked list. So it actually becomes more efficient very quickly. Even if you iterate only twice on this new list, it is more efficient than iterating twice on your linked list. The only caveat is that you consume much more memory, and you can have some desync between your linked list and your copy while you are processing it, because what you're using is really a copy, not a view on this linked list. At this point, you know one of the most important things about pointer-based structure: pointer chasing can kill your performances. And this is the case for all pointer-based structures, including all trees. Tri-trees, binary trees, red black trees. This is the case for skip lists and of course linked lists. So now the question is, do ArrayLists have caveats? And what are the impacts on performances? Are there use cases where linked list actually performs better than ArrayLists? So the answer is yes. ArrayLists do have caveats. There are actually 2 of them. First, inserting an element at a given position consists in first copying the rest of the array one cell to the right. This is an overhead that does not exist in linked lists because inserting a node just consists in adjusting the next and previous pointers, which looks much less complex. And by the way, deleting an element from an array list is the same. The rest of the array is copied one cell to the left so that no hole is left in the array. And second, adding an element at the end of an array list is not only about adding a reference in the cell of an array. Sometimes this array is full and it has to be copied in a larger array. And by the way, it can also happen when you are inserting an element at a given position. So what is the impact of these 2 internal mechanisms that ArrayList is using? Well, once again, there is only one way to find out: create a benchmark to measure that. So let us create a full ArrayList and measure the time it takes to add one element at the end of it, and the time it takes to insert an element in the middle of it. ArrayList uses a growing factor of 1.5. It means that every time it becomes full, it creates a larger array, 50% bigger than the previous one. If you take this overhead into account, it means that adding an element to an array list is actually not a complexity of big O of 1, it's more like big O of log of n. Okay, let us skip this one, it's not really relevant here. What is the price of resizing an array? That is, allocating this array and copying the previous one to the new one. So let us add an element at the end of a full array to trigger this resizing. Remember that adding an element at the end of an array list was a few nanoseconds. So as you can see, resizing this array actually takes quite some time. Half a microsecond for 1,000 elements array. As expected, this resizing is not free. If memory is not an issue in your application, preparing an array of the right size upfront to avoid this operation can be a performance improvement. Now, what is the price of copying this array to insert an element? Well, once again, this is something that you can measure, and as expected, it varies with the amount of elements you are going to move. And by the way, if you do both at the same time, inserting in a full array list, that will trigger a resizing, and you can see that the result is consistent with the two other operations. You basically add the two performance hits. So how does insertion at the beginning of the list compare to the performance of the linked list? Well, this operation is cheap on linked list, between 7 and 8 nanoseconds on this benchmark, plus it does not depend on the number of elements in your list, and it does not depend on the way your node objects have been created, whether they are stored in contiguous space in memory or randomly scattered all over the place doesn't make any difference. And the same goes for adding elements at the end of a linked list. The performances are stable between 9 and 12 nanoseconds. They do not depend on the number of elements of your list, nor on the way they have been added. So these are two use cases where linked list is really interesting and performs better than array list, operating at the beginning of the list or at the end of the list. The operation could be reading, inserting, or deleting that actually costs the same as inserting. This is all nice, but you may be wondering, are these really operations on the list structure? A collection where you have only access to the first and the last element is not called a collection anymore, it's called a stack or a queue. And indeed, linked lists are very good stack or queue implementations. When it comes to regular lists, not so good. They are always outperformed by array lists. How do ArrayList and LinkedList perform memory-wise? This one is a trick question, as different JVM handle memory differently, and a single JVM can have different strategies depending on the amount of memory it is running in. How can you measure the amount of memory an object is actually consuming? Well, there is a tool for that called Java Object Layout, developed by Alexei Shepelev, that is also developing JMH. And if you want to learn more about this tool, my friend Don Rab wrote an excellent blog post on how to use it on real-world use cases. All the links are in the description. In general, storing a given amount of objects in a linked list requires more memory than storing the same objects in an array list. There is actually a good reason for that. Each reference in a linked list is stored in a node object that also stores two other references, one to the previous node and the other to the next node. This typically requires 24 bytes because you need to add the header of this node object. The exact number can vary depending on your application. If your application consumes less than 32 gigabytes, this number is most of the time exact. For instance, for 1,000 objects, a linked list will consume a little more than 24 kilobytes of memory, where an array list only consumes a little less than 5 kilobytes. There is one use case, though, where storing your object in an array list is more costly. If you have only one object to store, then the array list you create has an array of size 10. This is how array list is working. And in that case, your array list consumes more memory than a linked list. 76 bytes versus 56 bytes. So if you have many such lists, then you can come across memory consumption issues. Let me put it in the other way. If you have an application that creates many array lists and you come across unexpected memory issues, then you should investigate more precisely how many objects your array lists are holding. It could be that you are actually creating almost empty array lists that eat up too much memory. If you're in that case, you still have several solutions. Using a linked list is one of them, but maybe you can also use one of the non-modifiable implementations that you can get with the list.off methods. These are more efficient than ArrayList and linked list, memory-wise, only 40 bytes for just one element. One last point on memory consumption. Because of the way it is working, a linked list always accommodates for the exact number of elements it needs to carry. There is no empty node in a linked list. On the other hand, ArrayList grows automatically when its internal array is full. It turns out that there is no mechanism in ArrayList that shrinks this array automatically when you remove elements. So if your application removes many elements from your array list, you may reach a situation where this internal array is large because it was needed at some point, but becomes almost empty, still consuming memory for nothing. In fact, an array list holds an array that can grow. It is copied in a larger array if needed, but this array is never copied to a smaller array. So if you run into memory issues, this is definitely a point that you also need to investigate. Fortunately, there is a trimToSize method defined on the ArrayList class, it's not on the list interface, that trims the capacity of its internal array to the size of your list. By the way, if you call trimToSize on a one-element array list, then it becomes smaller than the one-element linked list. You will immediately save memory by calling this method, but you will also have to grow your list again the next time you add an element to it. Okay, so let us wrap up all this. In a nutshell, ArrayList is a good implementation that outperforms linked list in almost all the classical list operations, at least when what you need is a regular list. It comes from the fact that a linked list is a pointer-based structure that suffers from pointer chasing. So iterating is costly, getting an element by its index is costly, which has an impact on all the classical operations, inserting, replacing, deleting. Even if these operations by themselves cost less on linked list than on ArrayList, the performances are killed by the fact that accessing the right element is super expensive due to pointer chasing. ArrayList are not so good at inserting because of this system.arrayCopy operation, but still mostly better than linked list. ArrayList has one caveat, resizing, that is costly. If you have enough memory, you can avoid resizing by creating array lists that are large enough to hold all the objects you need upfront. There is one case where linked list performs better than ArrayList. It's the case when you need to access only the first or the last element of your list. That is, what you need is actually a stack or a queue, not a regular list. And by the way, linked list indeed implements queue. One last point, keep in mind that a linked list consumes much more memory than an array list. One exception, a one-element linked list consumes less memory than a one-element array list. And one thing to keep in mind, an array list never shrinks. You can empty its internal array by calling remove or even by calling clear, but this array will stay there. You can fix this situation by calling trimToSize defined on the ArrayList class. And with this, I'm out of coffee. So that's it for today. Talk to you soon.